afternoon, and thank you for joining us for the 49th webinar in the Offshore Wind series, Learning from the Experts. I'm Peter Lyon, Senior Advisor with NYSERDA's Offshore Wind team, and it's my pleasure to be joined by today's expert, Walt Musial. Before I introduce our speaker, a few reminders for participants and some background on the webinar series. Next slide, please. Firstly, if you're experiencing any technical issues, please contact Adma Hawk at the email address on the bottom of the slide. The webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Expert series are available on NYSERDA's website at the address on the slide. All participants have been muted. We'll have time for Q&A following the presentation, so please use the Q&A function to submit your questions to all panelists. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavored to select Learning from the Expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you'd like to suggest a topic or speaker for a future webinar, you can email us at offshore-wind@nyserda.ny.gov or fill out a survey also available on our website. Please note that the views and opinions expressed in this presentation are those of the presenters. Next slide, please. It's now my pleasure to introduce you to Walt Musial. Walt is the Chief Engineer of Offshore Wind at the National Renewable Energy Laboratory, NREL, where he has worked for 36 years. In 2003, he initiated the Offshore Wind Energy Research Program at NREL, which focuses on a wide range of industry needs and critical technology challenges. He chairs the ACP Offshore Wind Standards Subcommittee and helped originate the National Offshore Wind R&D Consortium as their senior technical advisor. Previously, Walt developed and ran NREL's full-scale blade and drivetrain testing facilities for 15 years. He studied mechanical engineering at the University of Massachusetts Amherst, where he earned his bachelor's and master's degrees, specializing in energy conversion with a focus on wind energy engineering. He has over 120 publications and 3 patents. Thank you, and I'll now hand things over to our speaker.
Thank you, Peter. My pleasure to be here, and I'm going to share my screen now. And I'm going to probably need your feedback to...
And you are all set to go, Walt. It's a good view.
All right, perfect. Okay. Thanks, Peter. I'd just like to extend my thanks to NYSERDA for inviting me to this and giving me a chance to talk about this topic. I believe that this the scaling of offshore wind turbines has been a topic that is interesting and concerning maybe to many people, and I think that the industry is at a crossroads where we maybe need to understand this a little better, and I hope this will help contribute to the conversations that we'll be having over the next few years. So I'm going to just start by with this slide because I want to dispel a lot of the confusion that I've encountered in my experience when people talk about upscaling. There's actually 3 different ways that I refer to scale. One of them is the turbine scale, and that's how big the turbines get. And it's usually measured by the nameplate capacities of the generators that are on the turbines. And we're now, as everyone is probably aware, into a platform of 15 megawatt scale turbines. There's also project scale, which is different. Project scale is really the total nameplate capacity of the entire projects that's being built, regardless of the size of the turbines. And to get project scale, that is commercial scale, or sometimes talked about utility scale, we need large projects to get the costs down. So that's an important part, but it's totally different than turbine scale. And then market scale is really something that we need in order to demonstrate that we have the capacity and the volume in order to build enough machines to learn and mature the technologies that we're developing right now. So the cumulative sum of the policy commitments or the ambitions that we have made globally are, kind of reflect that market scale and the anticipated volume of production that there will be. And these scales, they don't all work together. So I'm going to try to break that down and sort that out for you. So the first one I'm going to talk about is really turbine scale, and maybe talk about the history of quickly. Because I could spend a whole conversation, whole hour talking about the history of turbines, because I lived through a lot of this. But this is just a slide to remind us that we've done a lot of upscaling, and the upscaling that has happened in the past has been amazing. The turbines shown on the left was taken in Tehachapi. I don't know when the photo was actually taken, but the turbines were installed in about 1985, and there's over 100 turbines in this picture. Those turbines could be replaced by that one turbine on the right side. That's a Siemens 11 megawatt machine. We took that picture, my colleague and friend Dennis Schroeder took that picture on September 11th this year. And that's one of the turbines that's going into Revolution 1, which will be serving power into Connecticut and Rhode Island. And so you can see the difference. That one machine could replace all of the machines on the left side. And if I look back on land-based wind, this chart on the left shows the size increase of the capacity of the land-based machines. And it does look like the machines keep increasing over time, but those increases have been fairly marginally made, and the scale had kind of settled out around 2 megawatts, and that's because, as shown in the figure on the picture on the right, the infrastructure to move the large components around to build land-based wind farms was constrained by the bridges, the road system, and the cranes that had to install those machines. So we kind of leveled out around 2 megawatts, although that increase has crept up, and that's really more due to the optimization of those machines as we get into slightly larger rotors, higher hub heights, and low specific power machines. So that stable size has allowed the land-based industry to industrialize and to realize the maturity of the product lines that they've been delivering. But those products also became the first technology platform for the offshore wind machines back in the early 2000s. And I'm going to just talk about that concept of technology platforms for a minute. So for 24 years, since Middelgrunden, when 2 megawatt machines were deployed in Denmark offshore, we've been commercializing the 2 megawatt machines on the first technology platform, and that's a definition that NREL is kind of using as a way to think of the steps that we take as we go from one configuration and one size envelope to another size envelope. And our definition is really the envelope of turbine technology and the proportionate infrastructure and supply chain scales that are necessary to with those capabilities to support the manufacture, installation, and service of that sector of the industry. So if the turbine size increases, so does all that supply chain and infrastructure. It all has to happen in unison. And the industry has kind of depended on that and relied on each other to go from one step to another. So we have Platform 1, which was based on the land-based 2 megawatt machines, which pretty much grew to the Siemens 3.6 megawatt, for example, which was one of the most prolific machines ever made. But we recognized really early on that we needed turbines that were designed for purpose for offshore wind. And so Platform 2 began really around the same time we started deploying offshore wind turbines, but it took a generation to fully develop those. But those machines had the permanent magnet generators, and they were much bigger. They started at 5 megawatts and then crept up to the 11 megawatt size, which we have now. Arguably, the 11 megawatt was the Siemens. That was that is the machine that's being deployed in a lot of the first projects offshore. But in Siemens' case, they made more turbines and more gradual steps. But we are now in building Platform 3, which is the 15 megawatt class machines, and that upscaling requires yet another round of infrastructure development, supply chain development, and turbine development. And we're still in the middle of that right now. So there's upscaling that happens incrementally to optimize turbines within a platform, and then there are these new platforms that we're seeing right now. This is a plot that takes all the projects that we could get the data from and plotting them on a time scale to show how that increase of turbine size has happened over the history of offshore wind. And you can see that there's a parabolic relationship there that goes into the present day, where we're now approaching a point where all the projects are committing to these 15 megawatt turbines that are just reaching the commercial stage. But the caution here is that while the land-based upscaling slowed because of the land-based infrastructure, offshore, we didn't have to slow down because there was no constraints until now, really, because the infrastructure now is being built, but there's limitations to how that infrastructure can further be developed to increase for further upscaling. There's in the United States, I think there's even greater limitations because we never built Platform 2. We're starting from scratch to build the 15 megawatt platform. So a lot of that infrastructure is more expensive. And we have the Jones Act, which limits our options in terms of vessels. We have to have US-based vessels. And so that Platform 3 turbine platform is still being built. And I need to make take my box away. Here it is. Sorry. So we're still building this platform, and these are the turbines that are serving that platform. All the main manufacturers of turbines, Siemens, Gamesa, GE, Vernova, and the Vestas 236 15 megawatt turbine are the main turbine manufacturers and turbines that will serve the projects of the United States in the next round of projects. And these turbines were enabled by technology advancements which happened over the last 2 decades, which we're all aware of. They aren't all wind energy advancements. Some of them are just technology advancements with computer technology and lightweight materials, innovations in manufacturing and load control from controls that we became proficient at, and then diagnostics for remote sensing and things like that have all led to this generation of turbines, which we're building now and will serve the industry well, I expect, in the future. This slide is just really to kind of review why we're doing that and what the benefits are for continued turbine upscaling. There's motivation because every time the turbine size gets bigger, fewer turbine positions are needed within a particular lease area, which means there is less balance of station costs to go with that. And that means fewer turbines, fewer foundations to install, less electrical cable, and fewer turbines to maintain, among other things. So those arguments hold true, and that's the foundation for the business case for most of this upscaling. We also see, though, that there's more energy from the taller towers. As the machines get bigger, they also get taller, and the figure on the right shows that those wind speeds do make a difference in how much energy gets produced. We also see that there's these reduced costs help developers win competitive procurement bids by bidding in with the larger turbines, and this has been going on since for 10 years now. In Europe and in the United States, it's kind of following true, where the larger machines, even though they don't yet exist, are helping developers win bids because they can bid in with the larger machines at a projected cost, and then those costs get turned into the prices that are negotiated in the power purchase agreements. We also see smaller seabed footprints, which means the turbines are wider apart, and they can and some of the navigation concerns can be alleviated or mitigated, and especially in places like Massachusetts, Rhode Island lease areas where turbine spacing was prescribed at 1 nautical mile. The larger turbines are the only way that we're going to increase capacity, the capacity density of the project, because the turbine spacings are fixed. So we're seeing that as a motivation to go to larger turbines. But let me talk about then what are the concerns of further upscaling. And the first one is in the blue box, is really talking about an old and well-known law of physics, called the square cube law. There was always this fear that because the turbine's energy output increases by the square of its rotor diameter, the turbine's weight is actually increasing by the cube of the diameter. So the turbine's getting heavier faster than it's making more energy. And that law of physics is being defied and offset by technology benefits that have been included in the development of these larger machines. But putting that aside for a while, as you get to larger and larger machines, we haven't found any hard limits that would limit turbine scaling, but there may be economic and practical limits that need to be considered. First of all, diminishing returns on reduced turbine positions means that as we get to larger and larger turbines, the percentage gained from going to one level to another is smaller. We also see that the turbines might be getting more expensive because of the square cube law. The heavier turbines mean more expensive turbines, and we don't have good data on this, but that's one of the things to be concerned about. We're seeing that the infrastructure investments are growing disproportionately because now all the supply chain has to be located near the ocean, which is more expensive in a lot of cases, and there's fewer sites to choose from. We're seeing that any new technology that gets introduced the bugs have to be worked out. That immature technology presents risks, which I'm going to talk about later. And then there's lost market opportunities too, because not all markets in the world, as the industry expands globally, can adapt to the larger and larger turbines. So we may be limiting ourselves in some places where, if, say, in 20, 30 years, we want to repower these foundations, if the turbines don't exist to do that, we can't reuse the infrastructure. Or island nations where they just don't have access to large ports, or non-industrialized countries where the development of those ports and vessels are probably unfeasible. So we have to consider that as we go. This is an example of what I mentioned just a minute ago, which is the diminishing returns. And you see that there's two lines vertically on this chart. One represents the 2 megawatt turbines that we started out with, and we came all the way to the 15 megawatt machines. And going through that upscaling, we gained about 7 times fewer turbine positions than we had at the start, say a Horns Rev type project. that kind of gain was significant, and it resulted in a large capital benefit, as shown on the right. But if we go to a larger machine, say a 20 megawatt machine, the gains are just a fraction of that, and the risks can be a lot greater. So there's, I think that my conclusion was that most of that low-hanging fruit has already been picked. We did really well getting to the 15 megawatt. The question is, should we go beyond that now, and is it worth it? There's a lot of reasons to consider that possibility. And one of the biggest reasons is the infrastructure costs. When we're having just kind of a coming into terms with this right now, but all aspects of the supply chain are dependent on turbine size. It's not just the turbine itself. There's the port infrastructure, the regulations and standards that need to be updated, the service and operation equipment, and the grid and electrical infrastructure to some degree. And then the manufacturing supply chain and the businesses that have to relocate and put their wharfs and access to the ocean into maybe in excess or less available real estate. So in just one example, the Oceanic Network estimated that there would need to be $36 billion of investment going into ports and infrastructure to build this next platform of 15 megawatt machines in the United States. So that's a substantial investment, and those are investments that are not part of the LCOE calculation that the developers have to make, and it's not under their control to make them. So that we have to make the market appealing enough to the investors to for those $36 million to come to fruition. So I'm going to use an example of another industry, which is the aircraft industry, to maybe use this as a cautionary tale. They've been working on jet airplanes for much longer than we've been working on wind turbines. But the 747 was developed in the 70s, and we always thought, oh wow, imagine how large airplanes will be by the time we get to the 2000s. Well, that really never happened. The development of the 747, it didn't get any bigger, and the A380 was really the largest passenger commercial airliner. Both of those jets have been discontinued because jumbo jets like this require large infrastructure to operate, and in particular, they required over 3,000 meters of runway space just to take off from airports, which limited where they could go. Smaller planes can serve regional airports where many passengers want to go, and the aircraft industry just wasn't able to fill the big jets. So the airport infrastructure favors the small aircraft. But we still need the larger aircraft for other things like international flights, cargo, and to serve major hubs. But in reality, and what has happened is that the aircraft industry has moved to a diversity of aircraft to serve diverse global markets. And if I just put up the fleet of United Airlines airplanes, they range from the 777, which is slightly smaller than the 747. The big jets aren't on this anymore. And then the smaller jets, they go down to these small commuter aircraft and everything in between. But most people are traveling on the 737 size airplanes now. And this is a kind of a maturity that the aircraft industry has gone through, and probably is still going through, where they realize that they need a variety of aircraft to serve all markets. So I'm going to move back to offshore wind. And here's another representation of the historic deployment of offshore wind turbines over time, representing the three platforms that I just talked about. So the yellow bars are the smallest platform, platform 1, which were adapted from land-based machines, the 2 megawatt to say 4 megawatt machines. The blue bars are the platform that evolved from the first generation of offshore machines, and that's started with the 5 megawatt machine and in up to arguably the 11 megawatt machines. And then it's the dividing line really was when GE deployed the first prototype in Rotterdam to start the process of the 15 megawatt class machines, which are the green bars. And most of that's in the future. But also on this chart is the cost curve that shows that costs were rising continuously until 2015, and then they started to come down, and we started to realize the benefits of this upscaling. But if we look at that and dissect it carefully, the commercialization of that 6 megawatt scale, platform 2 was partly responsible for generating that cost decline. But we also saw that the maturation of the supply chains for the 2 to 4 megawatt was really going. 80% of the machines deployed that year were in the platform 1, and they weren't necessarily that. So that cost decline wasn't entirely because the big machines came on. Only 20% of the market were those bigger machines. But what we were seeing is that it was competitive auctions in Europe that were using the 15 megawatt machines already to generate their cost projections and their price projections, and they were being awarded contracts based on those bigger machines that didn't exist yet. And then we were seeing also some competition from Asia. So this really started that cost curve and the decline of costs coming down. So and one thing I really want to point out is that there's technology risk in changing platforms. So there's also cost benefits. So we want to make sure that when we started with the 5 megawatt platform, the first prototype was deployed in Germany by Repower in 2005. But those machines really didn't start making a difference in the market until 2015, 10 years later. There was a lot of technology advancement and trial and error that went on in that technology platform in the late 2000s and early 2010s that led to commercialization of that platform. And we're kind of going through a process now where the 15 megawatt technology platform is beginning to go through that process of technology maturation, which started, as I said, in 2019, and it's continuing now. Of course, we have the experience of the previous platform to build on, but there's still a lot of learning to do with the infrastructure and the logistics and the turbine reliability that needs to still happen. And we'll be seeing that as we go. So I want to talk about those technology risks in introducing new technology. We have, so new turbines are more likely to have design and manufacturing oversights or defects because they haven't been tried yet, and we're building all new factories with new workers. This construction risk because there's new logistics and ships and the new ports that have to be developed, and the logistics depend on the on-time arrival of this new infrastructure and as it's being built. The supply chain is kind of the same way. You have new supply chain facilities that need to be built, and the vulnerabilities increase as the turbines get larger because the investments that have to be made into the supply chain and to the infrastructure system get greater, because now you have to locate those factories, which are much larger, on an ocean or a body of water where you can ship them from, and the number of suitable manufacturing locations are getting more scarce. So as you introduce this technology, the safety risk could also increase because there are situations that arise that are unforeseen, and those hazards could introduce safety risks as they have to be encountered without a procedure in place to deal with them. Operational risk is the same. You have field reliability problems that could arise due to the lack of understanding of the new technology, and those could result in higher failure rates. And the last one is really about, that time that it takes to mature that technology does cause some potential delays in deployment and increased risks that that maybe could slow the momentum down in the overall market. So we need to consider these things, and I want to kind of pivot now toward what I think is the big advantage to maturing the technology rather than continuing to upscale the technology. And I have an example of that I created based on my experience that I've worked through with a bunch of people, but I've kind of divided this into five stages, and I imagine this might be controversial because I think that experience from other OEMs might be quite different, but this really translates to the, or it's focused on the turbine, but it translates to the entire development of a new technology platform. When you start with the prototypes, and really we start before the prototypes because some of the bidding on the projects are happening before there's even a prototype in place. But the prototype gives you the visibility that the technology works. There's a proof of concept, and they generate their type certificates based off the prototype. And if you're familiar with the research scale of technology readiness, all prototypes would be considered TRL 9, which is the highest level that you can get to, which is technology readiness level 9. So none of these stages after that they're beyond a TRL 9. And I just wanted to put that in perspective. But the next stage that is followed logically would be the 0 series. So once you build the prototype and you know that it works, you go to a 0 series, which is a production line of maybe 5 to 10 turbines that are produced still by more elite technicians, and the designers are looking into it and doing a lot of oversight. And you have that experience from the prototype to fall back on solving a lot of the field problems, but you're still in a pre-commercial state. The infrastructure hasn't been built yet, and you have no market impact. The next leap is to stage 3, and this is a big leap because you have to get to commercial scale, and that's the utility scale projects, which give you the cost advantages of that scale of production. But in order to get there, you have to build the infrastructure. So floating wind is kind of going through this stage right now where you have to get to commercial scale. And the factory, you have factory-based industrial engineers, and you're working through the production glitches that you might have found in the early stage. But you need to consolidate the ports and the operations so that you can take advantage of that large-scale project, and that's starting to have a small market impact. As we go from commercialization to factory replication, now you're expanding and you're building multiple factories, and you have to train workers in remote locations, but you have this multi-year field experience, and that's one of the most important things, because now you know statistically what the failure rates are going to be on a lot of the projects, and you can afford to go in and do the retrofits and the design changes necessary to optimize the product. And that's starting to have a significant market impact. And then you get to this product maturation stage where everything is standardized, automated, and you really can benefit from the cost of learning, or the cost benefits of learning over time, and the learning curve, which I'm going to talk about. So first, now I'm going to go just talk more about the project scale, and I think it's an important concept that we've already seen in a lot of projects. But comparing this to Block Island, which was a 30 megawatt project, that project's going to be more expensive no matter what, because it's just a smaller project, and it doesn't have a lot of the equipment can't be amortized over the other parts of the project. When you go to South Fork, you're already much better because the project size is 4 times bigger than the Block Island, but you haven't really reached this commercial scale yet, which we're seeing now in say the construction of Revolution 1 or Sunrise, which are big projects at what I would call utility scale, and you're benefiting right away from the size of the machine. That doesn't mean the technology is mature yet. It just means that you're taking advantage of project size to bring costs down. There's still a long way to go to get to technology maturity. And that's the next section, which I want to talk about is how do you get to technology maturity? And in order to get there, you need the market size and market visibility to verify and to validate that to investors, especially, that the volume of production will be there, and you need to actually realize that. So this is really, and the figure is showing some substructures from Principal Power, but you need sufficient market scale in order to attract the investments necessary to build the infrastructure and supply chain just to reach that commercialization stage. And then that technology maturity comes from the industrialization of the supply chains and the massive amount of field experience that you need and the sustained innovation and learning that you get by building a lot of these machines. So market scale needs to be large enough for the investors to recover their investments and to feel that they will, that it will be sufficient to do that. So when I make this case or try to make this argument, I look to the global market. And one of the numbers that we use is, and I quote the TGS Market Intelligence. They've calculated that there are 807 gigawatts of commitments, or what they call ambitions, in the world market, where countries or states have committed to a certain amount of building offshore wind, either in hard commitments or soft targets. But that's a big number, 807. It's a big market if it comes to reality. And through our market report that NREL did, we've calculated there are actually 454 gigawatts in the project pipeline globally. If you just focus on the United States, we calculate that there are 80.5 gigawatts in the total US pipeline, with 65 projects that are shown in the maps on the right side. When we did our study this year in May, we're only counting projects that are actually commissioned and online. There was only 174 megawatts installed so far in the United States, but there's over 8 gigawatts approved now, and it's in multiple gigawatts under construction. And we were out looking at some of that. There's about 20 gigawatts that are in permitting, but we look at the hard procurement mandates that have been made by the states. There's 45 gigawatts of procurement mandates in 8 eastern states. So that's a pretty good market scale to lean on. And if you add up all the commitments as well as the soft targets that have been established by various states, like California has 25 gigawatts on their planning target, you get about 115 gigawatts of mandates and soft targets, which is a big enough number to say that we're going to have a market that's capable of maturing this technology. And so to get to this technology maturity, we have to work on this learning curve. And I know when we say learning curve, it sounds like a cliche. But the learning curve is actually a pretty well-known mathematical concept that says that the average cost of a unit decreases by a fixed percentage each time the production volume doubles. And when we're thinking about production volume, in this case, I'm thinking about the number of turbines that get made on a particular platform. So if we go from 100 turbines to 200 turbines, that's one doubling, and so on. And so this curve shows that trajectory of how that would look mathematically as we go down using a scale or a production percentage of 11.5, which is based on some analysis that NREL did. So this is just kind of a conceptual look at how costs can come down through technology and maturity. I'm just going to give you a few examples of other industries that have done this already, and some that are far beyond what I think wind can do. But here's the LED lighting, which everyone's familiar with, because the gray bar shows the market share of that, and that's pretty much everybody's house has LED lighting now. But those costs have come down from $12, $13 in just 14 years, or actually this is showing 2019. So in just 10 years, they reduced their costs from $12 to about 86 cents. And that's a huge drop. And that was done by just a huge volume production. Here's another example, which is maybe more closer to home, which is solar PV. Those prices have dropped 80% for projects since 2010. And that's based on the large drop in the production costs of the silicon solar panels that have now made solar one of the cheapest, competitive with land-based wind on the market. This is an example I hesitated to use, but I like it because people refer to it all the time. The Liberty ships in World War II were made during wartime at 18 different U.S. shipyards. They made 2,710 Liberty ships between 1941 and 1945. So 4 years, they made an average of 3 of these ships every day. The key thing here is that the production rate increased by a factor of 10 in just 2 years, because they had a huge learning curve to work from. The first ship took almost 3/4 of a year to make, while they were making an average of 1 ship every 39 days by 1943, with a workforce that was largely untrained. The woman shown in the upper right was a waitress, and they hired her to do the scaling of this welding. And this is on-the-job training, and they got good at it. The reason I like the comparison is because the displacements, the draft, the length of the spacing of the buoyancy columns, the cost, all kind of are on the same scale as the floating platforms for the 15 megawatt machines that we're building, or we would like to build today. And so this is a great comparison. If we built 2,700 platforms of 15 megawatt floating turbines, we'd have 40 gigawatts of deployment. So here's my last example, which is land-based wind. I start really from when things stabilized at 2 megawatts and moved down to the costs of 2022. There was a bump up in 2023 due to the inflation and a change in the market, which where they went to higher capacity or lower capacity factors, which wasn't explained very well. But this was a 63% cost reduction in 13 years due to the industrialization of the land-based platform, which was largely centered around the 2 megawatt machines. So what happens when we move to a new platform and we change the turbine technology substantially enough so that we have to build all new supply chain, all new infrastructure, and largely all new turbines? You're on this learning curve, which is the black line, and then you suddenly have to jump back up because there's been some learning loss, and you lose some time because you have to regroup. But you retain some of that learning because you know how to build wind turbines, you know what's supposed to happen, and you regain some of that. But you're now on a new learning trajectory. You've lost some time, and you have to start over a little bit. So there's some penalty that has to be paid for the promise of larger cost benefits that might be coming down the road. Or you could stay on the learning curve that you're on and achieve those cost benefits that I just described through experience, learning, and innovation that comes by optimizing the platform that you're already on. So now I'm going to shift to the role of China and what's happening there, because there's been a lot of press and a lot of people asking me questions about China, and I feel compelled to actually explore this a little bit more than what I'm going to show you now. But it's an obvious question, because the Chinese markets, this is just in the last few months, we've seen these headlines. Colossal 20 megawatt turbine is the largest on the planet for now. then Shanghai Electric unveils their 25 megawatt offshore wind turbine. One might think, well, this, is this real? Well, it continues. There's China debuts a record-smashing 26 megawatt offshore turbine, and this is another company, Dongfeng, and then the announcement that they were building this 35 megawatt dynamometer indicates that China intends to, or at least these companies at least intend to move to a platform that's in the 25 megawatt range. So what does that mean for the West and for the US and other Western countries, and how should we respond? Well, first of all, I just want to point out that China has been just this emerging player in the offshore wind market, and this chart shows how they've gone from almost nothing to becoming the dominant player worldwide, and their production often is greater than the rest of the world put together in terms of offshore wind deployment. So they have a big energy demand and a need, and they have a big market that's growing as well. Whoops, I'm going the wrong way. So when I look at the Chinese market, first we have to look at and compare their capabilities to the US and to other markets. There's the Chinese market is approximately, it could be 20 times greater than the United States in terms of its infrastructure requirements. And I base that on some of the details we have. It's not, there's not a lot of hard information, but for one example, their ports and infrastructure just cranking out ships. They have 20 installation vessels that are under construction now that can lift these big machines. Some of them can, at least. And the US has only one that can lift a 15 megawatt machine. China has this top-down approach, where a lot of these companies are state-owned, and they've integrated their military and civilian shipbuilding, so they're keeping the ports busy all the time. And at least in 2022, according to the UN, 92% of global shipbuilding came from either China, South Korea, and Japan, and this was dominated by China. China makes 60% of all the offshore wind turbines in the world, but 99% of those go to China. They're not exporting them. They're putting them in Chinese waters. So what does that mean for the US? Likely we're not going to be buying Chinese turbines at all in the US. Europe, though, the markets seem to be softening, and there's some concern that maybe the Chinese turbines could displace some of the European manufacturing. So that's something that I'm not an expert on, so I don't know if that's really going to happen. But I do know that to build and install a 20 megawatt turbine in the United States, it will be difficult if it's outside of Asia. And especially in the US, we don't have the ships, we don't have the ports that could do that. The new ports that are being developed right now have some headroom, but maybe not all of them have the same amount. So that has to be be weighed. I think that the takeaway from this slide really needs to be that Chinese can upscale and build this new platform for 25 megawatt turbines, but the rest of the world doesn't have to follow along. There can be a multi-scaled approach, a multi-market approach. We have never done this before, but I think as the industry matures, we're going to need to think about maintaining production at multiple levels of turbine scale in order to serve multiple markets. And I believe that would be one of my major takeaways. And I'll go through this upscaling takeaways list right now, and I just want to reiterate some of those points. First of all, we have a 15 megawatt capacity platform that's been developed, and we're building the enabling technology that defies those physical upscaling challenges, and we've succeeded in doing that. Further upscaling, though, will have diminishing returns, and we should think carefully about whether we want to continue to do that, or whether the 15 megawatt platform is big enough to achieve our cost goals, and I believe that it is. failure to account for the risks in changing or maturing the technology and building the larger infrastructure, and the increased time to market that may result from further upscaling is potentially biasing some of the expectations for cost reductions when developers go into a bidding process to compete with other developers in the market. So I think that we need to be more rational and focus on deliverability rather than on turbine size or absolute cost that's based on turbines that may or may not exist. The cost, I think that the cost reduction potential, as I've stated, is from industry learning and technology maturity is now greater than the benefits of further upscaling. That's my opinion, and this whole presentation is my opinion, by the way. Others may agree with me or not, but this is something that I put together. But the ultra large 20 megawatt plus machines that China's building, that might be suited for the Chinese market, and that might be a unique market that they need to reach their objectives, but they're not practical for the US market at this time. So there needs to be some collective industry-wide intelligence to manage this issue of upscaling, and it's not going to be a one-size-fits-all going forward. So I think that's where the industry is really at a crossroads. We need to avoid making the US supply chain that we're just starting to build obsolete before we even build it, and focus on domestic production. And while we still can address multiple markets that might exist in the global marketplace, such as South America or Africa or island nations, or repowering the platforms that we're building right now. So we might need these multiple turbine sizes in the future, just like United Airlines did, in order to serve this diverse global sub-markets and the market that we currently have in the United States. And that's the end of my presentation, folks. Thanks for listening.
Thanks, Walt, for that great and informative presentation. Really enjoyed the content there and the perspective on the scaling of turbines in these different markets. We have had a couple questions come in that I'll jump into now before we close out the series at 2 o'clock. So one of the questions, in regard to China, in other meetings, people have said that the wind turbine generators they are producing are having many faults and are not reliable. Can you address this concern? Are they growing too fast? Is this real? Have you heard anything solid to support these claims?
I haven't heard anything solid. There's a general lack of transparency with the information that comes out of the Chinese market. What I can say is that China has not traditionally been the innovator of turbine upscaling. Most of the upscaling has come from the European markets. So they're largely building these machines without the benefit of the rest of the industry. So time will tell if these turbines are what problems they might face. And I can expect that they would face a different set of problems than what we've already seen because of their scale and their size.
Great, thanks for that. Another question is in regards to maintenance. So with all the growth and expansion, what focus is being placed on maintenance and ensuring that replacement parts will be available for the existing or under construction wind turbines so they can exist for their entire 30+ year service life?
Yeah, I think that's one of the stages of technology maturity, is we develop the means to repair and service the machines in situ. And we have no experience with machines of this size yet, but I think we need the proper vessels and the proper service organizations onshore and offshore to be able to do that. There's what provisions are being made is it's the same as the development of the machine itself. We have to understand what parts are necessary to keep on hand for rapid service, and we have to be able to respond to field failures as they occur. And there will be field failures, and it's part of any machine's agree to have that.
It's interesting that the answer to that question really goes beyond the machine itself, but also, for instance, the available vessels that would be required, or lifting technologies in some cases, given the hub heights.
Absolutely, and the reliability, which is often assumed to be or overlooked. It's assumed to be as good as the previous generation, and I think that we can do better. But the early stage projects don't always achieve that reliability because there's unforeseen, unscheduled maintenance that has to happen.
Yeah, so thinking about lifting devices, as we build larger and larger rotors, do you see a need for high lift devices on blades to enhance the low wind speed range on the power curve? When, if ever, will it make sense for high lift devices to be added?
I'm
not quite sure.
High lift, we're talking about it. If we're talking about a vessel that can lift a blade and install it on a machine, or a system like I think Principal Power had did an in situ large component repair a couple months ago that drew some attention. Those are all necessary.
Nice. So one last question before we close things out. Does the scaling also increase the distance between turbines? And how is that taken into account for the area over which construction and O&M must occur and those costs?
Yes, turbine spacing is generally a non-dimensional distance that's based on rotor diameter. So we space the turbines further apart if the rotors get bigger, and that's not a hard rule. They could lots of developers have increased density by moving the turbines closer together, but they pay a penalty because of the lost energy because the wakes don't recover downstream from those turbines. So that's a trade-off that has to be factored into all the developers' concerns, as are many other concerns that I don't have time to go into. I would love to.
Well, again, thank you, Walt, for this great presentation. And thanks to, so I don't know if you want to stop sharing screens, we can get back to NYSERDA sharing. But thanks to everyone for joining us for this Learning from the Expert webinar. A reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next webinar in the series will be on Wednesday, December 11th. Mark Leborn with the World Bank will discuss considerations for deploying offshore wind in new markets, including international policy development. You can register for future webinars through our events page at wind.ny.gov. We also encourage you to check out past webinars in the series on NYSERDA's website and YouTube channel. If you have requests for future topics you'd like to hear about in this series, please email us at offshorewind@nyserda.ny.gov, or fill out the Learning from the Expert survey posted on our website. Thanks again for joining, and thank you again, Walt, and we will see you next time.